So still remember the wells, the well resistors? So the wells are not the only ones can be used as resistors, but you have used that, right? It's one of the options you can choose. But depending on the resistance of the resistor you need, you can choose different materials. So the N well is one of them, and we have calculated that the R square is a constant. So why? If this is a piece of N well, so if you do a cross-sectional view of the silicon wafer, that's the N well. And in some of the process, when you open up the PDK from the foundry, sometimes the name of that one is odd, like it's called tub. It just looks like a bathtub. So that's a well, right? And if we use that N well as a resistor, we know that R square is a constant, right? Why is that? R equals to rho times L over A, right? Then what? So if this is L, and the cross-sectional view, how to draw that? Like this. Like this. So this is A. A equals to what? T times, this is L, right? So this is the width. So this equals to rho times L over T W. So what's the constant? What are the constants here in this equation? Which ones are the constants? T. Okay, that's the thickness or the depth of the well. Cannot change it really much. So it's literally just the ratio of L over W. So which means if you have a 2L over 2W, it's just getting bigger, but still the same resistance. You don't know that happening, it's taking more space on the chip, right? So that's why R square is a constant. And if you have an N well, it's a pretty long well, like a long wire, but it's a well, then it has a delay. The reason is N well is an N material and this is a P material. Since we have learned semiconductors, we know the P junction, that's a P junction. What's going to happen for the P junction? Whenever you put them together, so what's going to be formed after a well? So the holes are moving from left to right, diffusion, right? So concentration gradient. So the holes are moving to here and electrons are moving to here. And the consequence is when the holes move to here, it neutralizes the electrons. And when the electrons move to here, it neutralizes the holes or deplete the holes and forms a depletion region. And now, what's the charge here? What's the polarity here? Negative. And here will be positive. What about here? Neutral. Why? You have a neutral silicon, you have a neutral phosphorus. Boom, still neutral, right? You cannot create charge just by combining material together. Then it's generating energy. Okay? But this one has energy inside. That's it's going to be a form of electric field, which is a VP. That's a built-in potential, right? It's the same concept. You got the P, you got an N. There's a P junction, and it's going to form a depletion region. There will be a depletion region in between these two materials. And since we have been talked about the property of the capacitance in the depletion region. So whenever you forward bias a diode, is the depletion region getting wider or smaller or narrower? Smaller. Why? How to remember it? When it's narrow enough. Yeah, so when it's narrow enough, so the electrons can just tunnel through. Okay, that's how to remember it. Okay, because the diode can only work when you forward bias it, right? So that's why it's getting narrower. But when you are looking at the charges, if you get the positive charge over here, because it's being forward biased, so electrons, it's been working before you connect the voltage source to the PN junction. It already formed that depletion region. But after you connect this one to the PN junction, that's the positive polarity. It's going to attract the electrons to here. Just taking these electrons away, it's getting thinner, right? And for this one, I mean, whatever, but I mean, getting thinner, getting wider, it has a capacitance. It has a capacitance. So there will be a capacitor, like built-in capacitor or something. Whenever you forward bias it, are you getting a larger capacitor or smaller capacitor? So C equals to sigma times L over A. So if you get larger A, you got smaller C, right? If you get longer distance, wait, A over D, right? Sorry. So larger A, larger cap. Longer distance, longer gap, bigger gap, smaller cap. Right? But there's a cap. So when you have this one forward biased compared to the reverse bias condition, so which one has a bigger cap? Yeah. Huh? Yeah, forward bias has a bigger cap because the distance is smaller. Okay, and that matters because when you are charging and discharging the diode, there will be a bandwidth limit because of the cap. It's charging and discharging. It's not like a resistor. It doesn't have any time delay. Whenever you got a cap, remember we have done that many times. You got a pulse, and that's it's called step response in signal processing. I mean, when I was in college, they always talking about like step response, how to calculate it, just tell you how to do the math. It's not making zero sense. It's just a time delay. Just say a time delay, right? They just won't tell you. They just like do the math for the whole semester and learn nothing. Anyway, so you know what's happening here. Step response is literally just you give a square wave to the system and it's being delayed. That's it. All right. Here's one question since we are here right now. So it's good to mention that since I was confused when I was in school. So if you have a square wave, definitely depends on the circuit. It has a different step response or time delay. If your circuit is fast enough, it is able to charge the full voltage potential, right? You can make that happen. How? If you have a RC circuit, here's VL, here's V in. So black is V in, the red one is VL. If it's not charging to the full range, what can you do to modify the circuit to make it happen, to make it charge to the full range? You're not changing the signal input, right? You're not changing the frequency of the input. You want to use a bigger resistor, smaller resistor? Yeah, it's very simple because you want to use a smaller resistor because smaller resistor will give you larger current. When you have a large current, you can charge and discharge the cap more efficiently, right? So you can fully charge to it quicker. And that's it. If you have a large resistor, it's limiting the current. When you are trying to fill up the cup, use a little straw, it takes forever. If you use a huge pipe, it takes like less than 1 second. It's going to spill out. So that's how you can understand this step response. However, whenever the input voltage, the input square wave becomes faster, still the same circuit, what's going to happen? So this red one is a step response of the circuit, right? You give a step, and then it's going to respond in that way. It's not going to care about like what's after it. So whenever you give that step, by just looking at the step, it's the same step. All right. But however, whenever the step rises to the voltage high, and then the output start rising, but the thing is, this one is going to start falling before this one is fully charged to the full voltage range. And then it's going to start discharging. So what's going to happen is it's going to rise to pretty much 50% and then start falling, right? And it's going to start oscillating like that all the time without charging to the full range. Does that make sense? Okay. Have you done any AC analysis for the sine wave? This is attenuation and time delay in circuit 1. Okay. Have you seen that sine wave time delay? So for the same RC circuit, if you got a sine wave input, what the output looks like? First, it's delayed. Second, it's being attenuated. Why? Because it's a voltage divider. An AC signal can pass the cap, and the cap has a resistance which is 1 over JW, J omega C. Right? That's a resistance. That's a impedance of the cap. So it's actually a voltage divider. So that's why VL is being attenuated. That's why it's being delayed and attenuated. Okay. So why is different? So let's make the input very slow. Can you let your sine wave fully charge to the full range? Why? But why I can do it with square wave? What's the difference? Like just because of the look, the square wave looks more handsome. Mm-hmm. I mean, what's the difference by looking at the shape? Why this one can even so if you make this super slow, okay, if you make the input super slow, that's a very slow square wave, and then you are looking at your step response, okay, and then you zoom out the signal, you couldn't even see that little delay. Is that correct? So it's like your output is duplicating the input and it's fully charged to the full range. Saying the sine wave can never do that. What's the problem here? We're not bringing up any equations. Not, yeah, that's the reason. It's never stay at the full voltage range for a period of time, and then it's gonna start falling. It's never stay there. How many points on the very top, the tip? 1. Just hit the top, then start falling. It's never able to reach that point because it's a voltage divider. If this one reaches a point here and the highest voltage here will be divided by this equation, okay? And the problem is why the DC voltage can eventually not getting divided. Why? It's very good to think about it. This is a really interesting topic. I mean, the teachers just won't tell you. You have to get confused and then start thinking about this for a few days and eventually get out like, oh, that's why. Huh? Yeah, that's right. Yeah. Did you get that? Why DC is not being divided? Because DC cannot pass the cap. Why AC is being divided? AC passed the cap. Is that correct? All right. Crystal clear on this right now. For a whole life. No questions on this anymore. I hope I had a professor like myself when I was in college. Okay, clear on this. And then let's keep talking about this unwell resistor. So here's how you model the time delay of the unwell resistor. I mean, you draw unwell, but you don't know, you are not dividing this unwell into different pieces, but when you are modeling or calculating the time delay, you are trying to divide them in different divisions. Because if I draw a pretty long unwell here, for example, so it literally looks like this. Grounded, because the P substrate are grounded. Cap, grounded, cap, grounded, cap, grounded. All right, so here's the unwell. And the reason we want to model it because the unwell is not a perfect conductor. It definitely has resistors. And if we use the R squares for each resistor, it becomes very easy to calculate the time delay. You know, the unwell is being used, that can be used as a resistor, but it's not an ideal resistor like you can get from the drawer in the electronics lab, because it has all the caps. It has a pin junction. So it's going to introduce time delay. So the unwells are going to introduce time delays. We are directly just using these resistors. They're not just pure resistors. It has a step response, okay? And these are C squares. So R squares are constant. What about C squares? Are they constants, C squares? No. Why? So C equals to A over L. So you are thinking about the rod shape, are unwell in there. And when you are forming a resistor, do we want to use a minimum length? So if you're looking from the top, that's the top view of the unwell. So what's this length should be? Oh, width, sorry, width. The minimum, yeah, whatever allows you to make the smallest one. It's not making sense to make it bigger because you have to make the length bigger as well. It's taking more space, right? So in that case, if you get a little square over here, and this can generate a C square, right? So underneath it, it has a C square from the N well to the P substrate. So is that a constant? It should be, right? Because they're using the same width everywhere. So what about, so R equals to what? Rho L over A. Okay, you want to memorize these two equations. So we got C squares and R squares. So what's the time delay for the circuit over here? How do you calculate it? Here's V in. So the way to do that is you have different points. That's A, point B, point C, for example. And so the time delay from here to point A is calculated as 0.7 R squared C squared. You just don't look at all the following circuits, right? Which makes sense. We're not modeling this one actually. So start from 3 resistors, 3 caps, right? That makes sense. You have 3 squares in total in this case. So that's a C square. Okay, so what about A to B? No, you are not calculating in that way. So how to calculate it? This is like, it can be tricky, but the method being provided on the CMOS book, the textbook of the class, so it's being calculated in this way. So T from here to A is definitely this, and from here to B, we always start from here. Why? So you start from here to here, you can get this, and then you calculate for TDB equals to 0.7. You got 2 R's to limit the current. So it's 2 R squared. And because this is another cap, it's but only one single cap. So it's another C squared. And here to TC, here to C is TDC, which is 0.7 times 3 times R squared times C squared. And how to deal with all these little time delay times. So the overall time delay from here to here would be TDA plus TDB plus TDC. Why we can calculate in that way? You are thinking like, hey, when you are trying to find out the time delay from here to B, why can't you just directly use 0.7 2R C? What about this cap? Same for this one. The time delay TDC from here to here. I'm just looking at the 3 resistors and this cap. So that's why it's 0.7 times 3 times R squared times C squared, but not looking at these 2 caps. I think this is something very similar to superposition. You just accumulating all the time delays because this cap has already been calculated here already. So you're adding them together eventually. So that's why when you are looking at this cap, you are not looking at this one. The time delay contribution from this one has been calculated. You are going to add that time delay later, at a later time. Intuitively, that's how I explain that. Okay. Otherwise, let me know how we can model that. You let me know. Okay. I don't know. This is the only way I know. All right. And I think that works if you simulate it in empty space. So if you have L squares, if you have L squares, so L is a length, right? So length usually is a number of how many squares you have. What's the time delay? TD, or the overall TD, L squares. So it becomes 0.7 R square C square. So starting from this, right? That's 1, 2, 3 until L. Is that correct? Just factor this thing out. It's adding all of them together and factor this out. So you're getting 1 plus 2 plus 3, right? And until L, so L squares in your unwell. And this equals to 0.7 R square C square. So what is this? Did you learn this anywhere? In middle school or high school? So what this equals to? Is that L times like 1 plus L over 2? And which is, let's assume the resistor is pretty long. So L is pretty much 1 plus L. And this becomes 0.7 times R square C square L square. And eventually you're getting 0.35 L square. All right, so that's the final equation to calculate the time delay of the unwell. All right, let's look at one example here. Estimate the time delay through 250 kilo ohms resistor, unwell resistor. So the width is 10, the length is 500. They're asking like which technology you are using, like 1 micron, 50 nano, or 180 TSMC. Does that matter? The cap of a 10 by 10 square is 5 femtofarad. So look at this equation we just derived. In order to calculate the delay, you need to know these, and this. Okay, do you know L? So what is L? Yeah, 500 over 10. So you have 50 squares. What is R square? Take it easy. The overall resistance is 250 kilo ohms, right? And there are 50 squares. So what's the resistance per square? Yeah. 5 kilo. So what is C square? Which is given, right? So this example is easier because it gives you the 10 by 10 square is 5 femto. So what if 5 by 5 is 5 femto? How about that? That's a good question. 10 by 10 is 5. 5 by 5, so if 5 by 5 is 5 femto, that's a given condition here. What's the C square in this case? Do you want to use the C square here or here? We are calculating the time delay for the N well, and the N well has a width of 10. So you want to use a C square of 10 because larger area has a larger cap. So C equals to and D is not changing because that's something in the wafer. It's not changing. It's already there, doped. So we know 5 by 5 is, so for example, here's a square, okay? So that's 5 by 5 is 5 femto. So 10 by 10 will be, you got 4 5s, 20 femto. And then plug in, okay? Find the delay. Any questions on this? Clear? Not clear? Any questions? C5 layers. So there's something can be very confusing because sometimes we draw the fused oxide on the top, but for the in real world, it's actually getting into the silicon substrate a little bit. I don't know how that was made. Depends on different technologies. They have different process. But you should realize that in real world, the oxide layer directly on the top of the silicon substrate is not like, for example, here's a substrate. So fused oxide, just silicon oxide, okay? It's FOX for short. So the FOX is not directly just sitting on the top. it's like this, getting into it a little bit. So how these layers are fabricated in the semiconductor industry? It's mysterious, right? It's very complicated. How that works? So originally there's a wafer, usually 18 inches wafer, and nothing on the top. So what's the first step? Spin coat. You have a spin coater, has a little vacuum at the bottom to hold the wafer, and you spin coat it with a material called photoresist. So there are two types of different photoresist materials. One is called the positive photoresist. Another one is negative. So in the semiconductor industry, they usually use a positive photoresist instead of negative. So what's the difference over here? So the material, the texture of the photoresist is like a honey texture. So you can buy bottles of photoresist. They are super expensive, like 500 ml. It's usually $1,000. So you place that wafer on the vacuum. The spin coater has a vacuum at the bottom. The chuck can hold it. Make sure it's in the middle, and then pour that photoresist in the middle, like a puddle in the middle of the wafer, and turn on the spin coater. Spin coat it. So you get a very uniform thin layer of photoresist on the top. Still honey material texture, and then put in the oven to cure it, so it becomes like a plastic texture. That material is very photosensitive, especially to UVs, ultraviolet. But also these lights also have UV component in there, not super strong UV, but you don't want to expose that wafer with a photoresist in anywhere that has a UV component in the room. Okay, so that's why usually they use the orange color or orange light in the clean room. Clean room is the place you can fabricate integrated circuits. Usually it's 1 cubic meter in the clean room. It has 100 level or 1,000 level, which means 100 level is 1 cubic meter has 100 particles, dust. And the 1,000 level is 1 cubic meter has 1,000 dust particles. You're wondering like how many dust particles we have over here in the classroom? 10 billion, right? So it's super clean. And with the orange light, so it's not damaging the photoresist. So the first step, spin coat it. And second step, apply the first layer of the mask. So what is a mask? You have a mask on our face. So the mask is something you can print, you can design the shape. Actually, you guys are drawing GDS files. You guys are drawing the layout, circuit layout. You think you are drawing circuits, you are drawing the mask. So what's happening is these circuit layouts will be printed out as a GDS2 file. It's a format can be directly printed out on the masks. So the mask can be printed on the glass plate, which is a more expensive mask material, the plate. And the cheaper ones can be just a plastic film, clear plastic film. And so for example, if you are using negative photoresist, whenever you draw, so after you print out the whole circuit, then whenever there's a wire, it shows clear on the mask. So spin coat, photoresist, that's a wafer, right? That's a photoresist. And you have a mask, which you draw all the features like wires, whatever you draw on that in a layout, okay? And for example, here's the mask. These are dark, just ink, right? So the ink is not a regular ink we have over here. It's just a different material, has all the metal particles, which can totally block the UV. but this is clear. This is a clear plastic or the glass plate. All right, and then I'm going to expose everything to UV. UV. So definitely these ones will block the UV because the photoresistant materials, the negative ones, are very sensitive to also positive ones as well, but here it's different. So whatever has been exposed to UV, the molecules inside are getting cross-linked. I don't know what that means in chemistry, but cross-linked, which means like they are getting more resistant. They are not more, they are totally resistant to another agent I'm going to use later after this process. Okay, so they will stay. So whatever exposed to the UV will stay on the wafer. Okay, so after that, after I use a mask to protect these areas, only expose this area with UV. And next step, I'm going to bring a beaker and use a chemical which stinks and toxic as well. You want to keep this material called developer inside the hood. You'll never take it out from the hood. So developer is an organic solvent. That's why you don't want to be in the biochemistry major, because people get cancer in their nose and in their lungs because they are doing organic chemistry experiments for over 10 years. They get a way higher chance than other people to get cancer. So organic solvents are really bad. Good here, good for the wafers. And so you take the mask away from the silicon wafer, and then immerse it inside a developer, which is going to remove all the unexposed photoresist, but only has only this part is going to stay. Okay. You're asking, like, why do we need a photoresist to stay on the top of the wafer? You must be wondering, like, why? They're going to protect something else. Yeah. So what's going to happen is actually it's not starting with, this is not doing anything, right? So what if you have another layer? I can deposit a metal layer, like a metal one, for example, and then I do photoresist. And then I do mask, and then UV, all right, then developer. Okay, so what's gonna happen after that, after developer, is I still have this metal layer on the top because the developer is an organic solvent, it's not an agent. So I still have metal one here. And now I get another layer because here this part will stay. Okay, and then I just throw everything into an acid. Or agent is all different types of agent can be used over here. So all the metal exposed to the agent will go away. So eventually you are getting a photoresist, and underneath is that's metal one, right? That's metal one. So that's a wire I want to keep on the circuit. That's a circuit wire, for example. Okay, that's one of the traces on the circuit. And you're asking, like, you still have this photoresist on top, right? I don't need that in a circuit. I have to throw the entire thing into another beaker. So a stripper. It's going to strip this away from the top of the metal, and you only have a wafer with a metal, so get a circuit, right? So the real process is way more complicated than this. The thing is, just keep doing this kind of exposure, spin coating, because C5 has many layers. For TSMC 180 has, so for the C5 we are using only has 3 metal layers. And for the smaller ones, like 20 nanometer technology probably has like more than 6. I don't know how many because it's in NDA. So I still have a couple minutes. Let's draw the layers on the paper. Piece up. That's Fox. Field oxide. Yeah, insulator 1. Which has polysilicon, the gate. And another insulator layer. What is in there? Metal 1. Next. Testing if you're still awake. So you can have metal 3 over here, right? So for example, that's a metal 3 wire. And you need an opening. Why? You don't want to close everything inside. So you cannot get the signal out and in. So metal 3, usually whatever input, output. If you have an N plus here, right? And you have to drill the holes. So these are called vias. And then, keep doing this. And eventually you can connect all the signals to metal 3. The reason you have to connect everything to metal 3 is because all the bonding wires are being connected to metal 3. So the bonding wires are super thin. You couldn't even visualize it. And you have to use a special tool called wire bonder to do it. And we have a wire bonder in the lab, in my lab. If you want to do it, we'll have a chance to get you guys trained on how to bond the wires to metal 3 at the pads. Look at one of the examples on the website. Sorry. You have a question? What's that? Yeah. No, you are not. So the way you are doing that is metal 1, right? Have to get a via here. Oh, sorry. Have to get a via here, and you can use metal 2 to connect to metal 1. But not directly, yeah, you are right. You don't want to just directly stacking or piling up all the vias on top of each other. You can do that theoretically, but it's going to reduce the yield, which is a rate you can get a good chip. Just not a good practice. Usually you don't do that. So yield is very critical. A lot of foundries can make the same technology chip. For example, 20 nanometer technology, probably in one of the labs in Stanford University, the graduate student can also make a 20 nanometer node or little NMOS in the lab. So what's the difference from that lab to the TSMC 20 nanometer foundry? Critical. They have a wafer has like 200 chips on the wafer fabricated, and there are like 190 are good chips. And for you're doing in the lab, there's only 1 or 2. So the cost will be like 100 times higher. Definitely you cannot sell the chip to anywhere. So that's critical. I'm not talking about the extreme cases like that, TSMC 190, and the lab operating by a graduate student is getting 2. I'm talking about TSMC and another foundry, for example, Global Foundry or somewhere else, also a big company, but just making 150, then you're done. You're out from the business. 190 can compete with 190, but not 150. So yield is very critical, right? See you on Monday.